Hello students, this is Chandrasekhar. Very good morning to all of you. Welcome to Tungal online classes. Today we have to discuss about the Norton's theorem. Yesterday it was already discussed about Thevenin's theorem. Okay, again we have to recall the Thevenin's theorem. See here, Thevenin's theorem, Norton's theorem, both are same, but a little bit difference it is there. And the Thevenin's theorem, what it is giving means any complicated network converted into single voltage source in series impedance. That means with that of two components, the total complicated network it will be replaced. Whereas the Norton's theorem, what it is giving means here any complicated network it will be converted into single current source and a parallel impedance. So parallel impedance also called as admittance. So that is only the difference. In the Thevenin's theorem, voltage source and series impedance, whereas in the Norton's theorem, the current source, that means single current source in parallel with the single impedance. That is only the difference in between them, and remaining as it is. That means Thevenin's and Norton's, what it is giving means that voltage source how to convert the current source. That is the main advantage to learn about this Thevenin's theorems and Norton's theorems. Now coming to the statement. In any two-terminal linear network containing sources of EMFs E and impedances Z can be replaced by a single current source IN in parallel with the single impedance. See here, the red letters, what is indicating that only the change. So Thevenin's theorem, Norton's theorem, same to same. But here in the Thevenin's theorem, in place of the current voltage it is there. In place of here E Thevenin's it is there. E Thevenin is replaced by IN. And here this is series impedance, but here the parallel impedance. That is only the statement change. Okay. So in any two-terminal linear network, so any two-terminal linear network you take, who is having many number of sources, how many number of sources are there, and also how many number of impedances also are there, that all sources of impedances and replaced by a single current source IN in parallel with a single impedance Zn. So this is about the statement. Now we have to define what is IN and what is Zn. Norton current means what, and also Norton's impedance means what, that we have to determine. So the second statement, what it is giving here, Norton's current, determination of Norton's current. So Norton's current, the current IN of the current source is the current measured at the short circuited terminals. See here, where in the Thevenin's theorem, short means open circuited, voltage source means open circuited, current source means short circuited. Remember perfectly here. So this is the current source, that's why short circuited, right? So the current IN of the current source is current measured at the short circuited terminals of the network. Whereas Norton's impedance, determination of Norton's impedance means the parallel impedance is the impedance measured between the terminals. So AB terminals, when all the internal sources of EMFs are replaced by their internal impedances, same to same. This will not be changed, only except parallel, all as it is. The Thevenin's theorem and Norton's theorem same to same, except these, what it was given the red marking, that only you have to change. That means series converted into parallel, IN converted into E Thevenin's, current converted into voltage source. Likewise here you have to make some adjustments, means the Thevenin's theorem converted into the Norton's theorem. Okay, so first of all, first statement here we will take. In the first statement, what was given, in any two-terminal linear network containing sources, I am taking one source. EMFs, okay, of EMFs E and impedances Z, 1, 2, 3. In between AB terminals, I am taking 3 impedances Z. So now this total circuit can be replaced by a single current source. See here, this is the single current source. Single current source, what it is here? IN. and total Z1, Z3, Z1, Z2, Z3, three impedances are there. These three impedances are replaced by Zn, Nortons. That means parallel with the single impedance. This is the parallel combination. So for this complicated network, this one is the simplified network. It was given, right? Now how to determine this one? So determination also in the statement itself it was given. How to determine the Norton's current and how to determine the Norton's impedance. Okay, now listen me. What is the Norton's? So Norton's current circuit how? The current IN of the current source is current measured at the short circuited current. Okay, so that is here this is the complicated network you take. In that complicated network this is the E and this one Z1, this is Z2 and here this one is Z3 and here this one is the terminals AB. Okay, now what he has given, the current IN of the current source is current measured at the short circuited terminals. This AB terminals means AB. This AB terminals of the network can be short circuited. Short circuited means this one like that here. So this is called as short circuited. Okay, short circuited. So in the short circuit here you have to determine the value of Norton's current, whereas these are the values of Z1, Z2 and this one is Z3, right? So this is plus minus the current it is flowing. Let us suppose here in this one I1 current flows, let us suppose, and here in this one IN current is flowing in this manner. So the current it is flowing IN as shown in the diagram. So this is IN whereas this one is I1. Okay, so I1 this is the direction flowing whereas IN is reverse direction. If I am following the I1 then I1 is the positive whereas IN is the negative. Then I1 minus IN here you have to take. Okay, so this is the circuit diagram to determine the Norton's current. So let us suppose here this one is determination of Norton's current. Next, how to determine the Zn? That means the Zn Norton's impedance. How to determine? What was given here? The parallel impedance is the impedance measured between the terminals. So again you have to take the terminals. What it is? This is Z1, this is Z2 and here this is Z3. The parallel impedance is the impedance measured between the terminals. So terminals means AB. When all the internal sources of EMFs are replaced by their internal impedances. So here energy source is there now. This energy source was replaced by its internal impedance means Z1. So this is the Z1 internal impedance. So energy source replaced by Z1 only. And here this is Z3 and this one is Z2. Now you have to measure what it is, what you need, Z Nortons you have to measure here, right? So by means of these two, what we have, these two, the final circuit what we have here is equivalent to completely what the circuit we have, this is the resultant circuit. So that means I Nortons means this is I Nortons and this one is the parallel impedance and this is the AB terminals, right? So this is the complicated network. This complicated network it will be replaced by using current source. This current source how much it is here? IN is equivalent to E Thevenin's divided by Z Thevenin's. E Thevenin's divided by Z Thevenin's. I will prove next. Okay, and next here this one is this is called as the Zn and the load ZL. This is the ZL, right? Now let us suppose here in this one, let us suppose here this one is the current IN, I Norton's current, here it is flowing, and this one is the IL, load current, IL, here it is flowing. In this manner here we will take, right? So now we have to solve these three circuits, means then we have to give the proof for the Norton's theorem. First you have to determine the IN value, substitute here, determine the ZN value, substitute here, and finally you got how much the load current it is flowing within this one. That is about our aim. Okay, now see here, first of all we have to determine the determination of, right, so the determination of IN, how we have to determine, just you see here. So apply Kirchhoff's voltage law like that here, A, B, C, D, E, F. So let us suppose here these are A dash, B dash, A dash, B dash you take. Then here, so apply Kirchhoff's voltage law for A, B, E, F, A network. So the loop. Then what happened here in this one? You have to apply the transition direction. So let us suppose here this is the transition direction. This one is the transition direction. So due to this transition direction, what happened here? The direction of conventional flow of current direction and transition direction both same. That's why plus E. So what the formula? Sigma E is equal to sigma IR plus, okay, sigma E plus sigma IR is equivalent to 0. Okay, so that sigma E means plus E, only one energy source it is there, hence energy sources completed in this loop. Next, here you are following this direction, means the transition direction, conventional flow of current direction is same, both are same here. That's why it will be considered as minus I1 Z1, minus I1 Z1. Okay, next here in this one, it will be I1 minus IN. Why we are taking I1 minus IN? So this is the energy source, highest energy source. I1 current is always greater than the IN. That's why you should follow the direction of I1. So that I1, this is the direction I am following I1, but Norton's current it is flowing in this direction, reverse. Hence I1 is the plus, IN is the minus. I1 minus IN is the current flowing through the branch Z3. Hence we are taking I1 minus IN. So therefore now we are following this I1 minus IN. But it is, both are same direction or not? Here both are same direction. That's why minus I1 minus IN, what it is? The Z3. So loop completed, hence it becomes 0. Right? So that now simplify, E minus I1, what it is there here? I1 Z1 plus Z3. This is minus of minus plus IN Z3 is equivalent to 0. Then here we say that here this is E is equivalent to, how we have to write? I1 Z1 plus Z3 minus IN Z3. Let us suppose here this is the expression 1. Next, now again apply Kirchhoff's voltage law for what the loop? B, C, D, E, B. Right? B, C, okay, B, C, D, E, B. B, C, D, E, B. Loop. So again the same formula here you take, sigma E plus sigma IR is equal to 0 is the Kirchhoff's voltage law. Is there any energy sources in this one? There are no energy sources. That's why it is 0. Okay. And next, now coming to the transition direction. So transition direction, how we are taking here? This is the transition direction. This is the transition direction. Right? This is the transition direction. For this transition direction, you start from here. What it is? The same, both are having the same direction. So this same direction means what we are taking here? Minus IN Z2. minus in Z2, and here nothing is there, here no branch. Again come to this branch, I1 minus in, this is the direction, so this one is the direction, this is the direction of I1 minus in, but you are following, this is the transition direction, both are in reverse. Reverse means then you have to take plus I1 minus in into Z3. Okay, now this will be, how we have to write, this will be equating to 0. Now we have to write I1 minus, okay, I1 Z3, this is I1 Z3, and minus in common. Minus in common means what we have here, Z2 minus Z3 means minus already common, that's why plus Z3 is equivalent to 0. So from this one, how we have to write, I1 is equivalent to I1 is equivalent to in Z2 plus Z3 whole divided by Z3. Let us suppose here this one is the equation number 2. So these are the loop equations. Now you have to submit the result from the second expression into the first one. Then how much we got? So then 2 in 1 implies 2 in 1 implies how much it is here? E is equivalent to, so E is equivalent to I1 means how much it is here? in Z2 plus Z3 whole by Z3 into Z1 plus Z3 minus in Z3, okay, minus in Z3. This is for right. Now simplify this one. Then what we got here? E is equal to in is the common factor. In common factor, here in is there. So then how we have to write Z1 Z2. So Z1 Z2, next Z1 Z3, Z1 Z3, next Z2 Z3, Z2 Z3 plus Z3 square, multiply minus this LCM, you do that, in Z3 square, in already common, Z3 square whole divided by Z3 we got. So this Z3 square cancelled, then I Norton's is equivalent to how much we got finally? I Norton's is equivalent to EZ3 whole divided by EZ3 divided by Z1 Z2 plus Z1 Z2 plus Z2 Z3 plus Z3 Z1. So this is the expression for Norton's equation. That is the formula here. So in is equal to what we got here? In is equal to EZ3 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1. Then Norton's current, determination of Norton's current has completed. In this one, what you come to know means, first of all you have the command about Kirchhoff's voltage law. So for that loop equations, if you can able to perfectly apply means, then either the Thevenin's theorem or the Norton's theorem or superposition theorem, whatever the theorem you can able to prepare, you can able to understand very easily, right? So now we have to concentrate about to derive the expression for Zn, right? So that means Norton's impedance we have to calculate. So let us suppose here this is the Norton's impedance. In the Norton's impedance, just you see, yesterday I told, so this is the terminal 1, terminal 2, 1, 2 terminals. Next for Z3, this is one terminal, this is the second terminal. For Z3, this is first terminal and this is for a second terminal. Now Z1, Z2 you see, so first terminal of Z1 connected to second terminal of Z2, and similarly first terminal of Z2, second terminal of Z1 both are connected each other. That is called as parallel combination. So how we have to write? For this parallel combination, Z2 is in series. Hence we have to write Zn is equivalent to Z2 plus Z1 parallel Z3. You have to write in this manner. So what is the parallel combination formula? 1 by Z is equal to 1 by Z1 plus 1 by Z2. If the two resistors, that means two impedances, are in parallel, then the resultant resistance or impedance is Z1 Z2 by Z1 plus Z2. So that is the formula we are following. Z1 Z3 means Z1 Z3 divided by Z1 plus Z3. That is the formula. Okay, and here this is the Zn. Now it was completed the, so if you want to prove that means, then here I am telling that 1 by Zn. So that means this is, you take here. So Z1 parallel to Z3 is equivalent to 1 by Z1 plus 1 by Z3. Right? So Z1 Z3 Z1 plus Z3. So this is the 1 by resultant. Then Z resultant is equal to Z1 Z3 divided by Z1 plus Z3. In that manner we are doing. Right? Then so 2 has completed. Now last one, what it is here? The Norton's equivalent circuit. So IN substitute here and Z Norton substitute here in the parallel impedance circuit. Then what we got? This is the equivalent circuit we got. Now this equivalent circuit, from this equivalent circuit, what we have here? On simplification we got, just you see here, this I want to get this okay, what it is here? IL. This is the current IL, here it is flowing, and this one is the I1, I Norton's. Right? Let us suppose here this one is the load voltage VL you take. Then the load current across the ZL I want. Okay, so IL is equivalent to V by R. Ohm's law apply here. VL by Z. This directly Ohm's law I applied. IL is equal to VL by ZL. Right? Now here VL means, what is the here VL, it was not given directly. Right? So that's why. Okay, now see here. Now we have to determine the value of VL. So that means voltage across the load resistance, load impedance ZL is how much it is. Again you have to apply the Ohm's law. V is equal to I into R. So VL is equal to, I means the Norton's current. This one is the energy source current. Here the energy source not there in this one. That's why the current due to the energy source only it is flowing to the second circuit. Hence you have to take V is equal to IR, means VL is equal to IN into Z result. Z result means what? The combination of these two are in parallel. That parallel combination you have to submit here. So first you have to follow the resistance, that means impedances are in parallel. Then this is the formula you have to apply, 1 by Z1 plus 1 by Z3. That means 1 by Zn plus 1 by Z3. So that's why VL is equivalent to IN. Z result means what? Zn ZL. So Zn parallel to ZL. So therefore IN, what we have here? The same formula. If Z1 Z3 are parallel, Z1 Z3 by Z1 plus Z3 is the formula. The same formula you may continue here also. Zn ZL divided by Zn plus ZL, that is the formula for VL. Let us suppose here this one is 1, let this is the second expression. So now 2 in 1 implies, what we got here? So therefore 2 in 1 implies IL is equivalent to, how much we got here? VL. So 1 by ZL, here 1 by ZL is there. VL value how much? IN into Zn ZL divided by Zn plus ZL. Right? So here in this one any cancellation? Here ZL, here ZL, both are cancelled each other, means then what answer it is? IL is equivalent to IN Zn by IN plus Zn. Have you got it? So these are the formulas should remember here. What it is? So let us suppose I Nortons, this one is the primary one and this one is the second Roman, and IL, so let this one is the third Roman. Here you take those values. Okay, now see here these three equations 1 2 Roman 1 Roman 2 Roman 3 are very important. So now we are giving the last, that equivalent circuit. So now you see here this is the equivalent circuit. So from this equivalent circuit what we come to know here, IN is equal to E Thevenin's by Z Thevenin's, E Thevenin's by Z Thevenin's, that only here. But from the equivalent circuit we have IN is equal to E Thevenin's by Z Thevenin's. Let us suppose here this is equation A you take. And next, already Thevenin's theorem we already solved. So from the Thevenin's theorem what we have, the load current. So load current IL is equal to what the formula we got? IL is equal to E Thevenin's divided by Z Thevenin's by ZL. So IL is equal to E Thevenin's divided by Z Thevenin's plus ZL. You know that. So for Z Thevenin's, otherwise Z Norton's, the same procedure we are following. Hence E that Z Norton's is equal to Z Thevenin's. Both are same. There is no change. Hence Z Thevenin's replaced by Z Norton's. Then here I am writing E Thevenin's by Z Norton's plus ZL. That is the IL value. Right? So from this one here I am writing. Shall I write here IN is equal to E Thevenin's by Z Thevenin's, means E Thevenin's I am going to replace IN into Z Thevenin's, that is IN into Z Norton's. So this is the E Thevenin's value. Let here this is B and this one is the C. Now B into C implies, B in C implies IL is equivalent to E Thevenin's, means how much nana here? E Thevenin's is equivalent to IN Zn divided by how much we got? Zn plus ZL. So see here this is the Roman 1. So now by using Thevenin's theorem the Norton's network converted into the current source. So what the Thevenin's theorem here? IL is equal to E Thevenin's by Z Thevenin's plus ZL. So in the Z Thevenin's by ZL, that means in the E Thevenin's already we come to know here E Thevenin's means I Norton's is equal to E Thevenin's by Z Thevenin's. From that E Thevenin's is equal to IN Zn we wrote. So now replace E Thevenin's by IN Zn. Now equation B substituted into the equation C. What we have here? IL is equal to IN Zn divided by Zn plus ZL. So what the equivalent network we have here? From the equivalent network, this is the equivalent network. From the equivalent network we got IL is equivalent to IN Zn divided by IN plus ZL. So here also from the practical network what we come to know here? IL is equivalent to IN Zn divided by Zn plus ZL. Right? So this one is Zn plus ZL. Okay, this is Zn. So then 3 and 4 implies, right? So from 3 and 4 implies what we come to know here? So that IL is equal to IL dash. Let us suppose here this one is IL, this one is IL dash. Okay, so then IL dash, that means this is from Thevenin's theorem, that means this is the practical and here this one is the theoretical. So theoretical proof IL is equivalent to the practical proof for IL. Both are equal. So IL is equivalent to IL dash is equivalent to IN Zn divided by Zn plus ZL. Hence the theorem. So this is about the Norton's theorem. Right? So thank you very much.